Let's talk about acid-base theories. By theories, I really mean working definitions. So we've got several definitions that come to us through the history of chemistry for what is an acid and what is a base. Nowadays, we have this understanding of strong acids and strong bases lying on opposite ends of a continuum of acidity, with all compounds lying somewhere along this line. Water, fairly neutral, orange juice, Coke, etc., being fairly acidic, Drano that we use to clean our toilets being fairly basic, etc., etc. But we haven't always had that understanding of acids and bases being connected to one another. Your earliest understandings of acids as a category of matter would be things which tasted sour, for example. I mean, who would taste your chemicals nowadays? But long ago, that was part and parcel of how you characterized any chemical compound, was what it tasted like and what it smelled like. So what is our first chemical definition of an acid? We have to go back to ionization theory to really understand what was going on. Ionization theory. How do we know that sodium chloride, when you dissolve it in water, dissociates into sodium +1 and chloride -1 ions? How do we know that? Well, it was demonstrated through conductivity measurements. The fact that if you had a circuit, and here's my battery, and here's my cathode, and here's my anode, and you put a light bulb in that circuit, and you made that circuit have to go through some aqueous solution in order to be completed. Let's say this is a beaker of water here. People took different substances one at a time and dissolved substance X in this beaker of water. And depending on what that substance was, some substances would allow the flow of electricity, and you would see the light bulb light up. Other substances would not. So things which did allow the flow of electricity they were defined as electrolytes, and they included things like sodium chloride, sulfuric acid, nitric acid. Non-electrolytes included things like sugar, glycerin. And now we have an understanding that non-electrolytes do not dissociate. They are neutral molecules, and when they dissolve in water, they remain neutral molecules. Electrolytes will dissociate into positively and negatively charged ions. So let's focus on this electrolyte category, because we're still working toward what was Arrhenius's definition of acid versus base. So bear in mind that it was Arrhenius who discovered this difference between electrolytes and non-electrolytes and first really articulated it. And this was actually when he was still a student in Sweden. This was in the late 1800s. So further characterizing these electrolytes, Arrhenius noticed that some solutions were what we could call chemically active, and other solutions were chemically pretty inert. What do we mean by chemically active versus chemically inert? Well, what do we mean by chemically active versus chemically inert? Well, let's say I was to stick my finger in one of the following 1 molar solutions. Solution 1, solution 2, or solution 3. Which one would you prefer to stick your finger into? And hold it there for a minute. Hopefully you said solution 3, the 1 molar solution of sodium chloride. Why? Because sodium chloride isn't likely to cause chemical changes to the molecules in my finger, whereas I would be very likely to see changes and a bit of pain if I were to stick my finger in the HCl or the NaOH solution. So these would be chemically active, we could say. The inactive solutions, Arrhenius classified as what he called salts. And among the active solutions, he classified them as either acids or bases. So Arrhenius defined an acid as any substance which produced H plus when dissolved in water, and a base as any substance which produced OH minus when dissolved in water. So what is the key limitation here? When dissolved in water. So this is organic chemistry class. We are not often going to be doing things in water as our solvent. A lot of times we're going to have some sort of organic compound as our solvent. So this definition is limited to aqueous solutions. And it's also limited to substances which produce H plus or OH minus. So for example, ammonia, which we know is a base, would have a hard time being classified by the Arrhenius definition. Let's expand our definition a little bit. First, we're going to talk about Brønsted-Lowry acids and bases. Brønsted and Lowry were two separate chemists who independently developed the same definition for acids and bases. They said that an acid was anything which donated H plus. And by H plus, keep in mind that H plus in chemistry is synonymous with proton. Why? Because you think about what a neutral hydrogen atom looks like. It's a proton with an electron floating around. So if you take the electron off, you get a positive charge and you get a bare proton. So H plus is synonymous with proton. Keep that in mind. So Brønsted-Lowry acid is a proton donor, and a Brønsted-Lowry base is a proton acceptor. If you were to take the same acid, hydrochloric acid, and dissolve it in, say, ethanol, you would get some degree of dissociation, just like in water, except now the proton is going on to the oxygen in ethanol. So here we would consider the ethanol to be a proton acceptor because it has collected that proton, this one right here, and used one of its lone pairs to bond with it. And we could call hydrochloric acid the proton donor because it has ended up giving up a proton to the Brønsted-Lewis base. Okay, but what is the limitation of this definition? It requires that we have H plus being involved. And H plus is not always involved. Protons are not always involved in acid-base reactions. So a more encompassing definition is to look at, rather than the movement of the positively charged has to be a hydrogen nucleus, let's look at the movement of electrons instead. And that is what Gilbert Lewis proposed with Lewis theory of acids and bases. And he proposed this also in 1923. So if we look at the above equation, we could consider either that hydrochloric acid is donating a proton, or we could say that hydrochloric acid is accepting a pair of electrons. Likewise, we could say that ethanol is accepting a proton nucleus, or a proton, or we could say that ethanol is donating a pair of electrons. So you see where we're going with this. A Lewis acid is any compound which accepts electron density, and a Lewis base is going to be a compound which donates electron density. Another way that we could phrase this is that the hydrochloric acid is electrophilic. Electro referring to the electrons, philic, loving of electrons. We could also refer to the Lewis base as nucleophilic. These are adjectives, by the way. So the acid is a noun, electrophilic is an adjective that would describe a Lewis acid. So what do we mean by nucleophilic for a Lewis base? Well, this pair of electrons on the oxygen here is really attracted to, if you think about what that HCl looks like, here are our core charges. And that lone pair we're just going to call ethanol base here. This pair of electrons is really hanging out mostly, spending most of its time on the chlorine side of this bond. So what is being seen here is a great big delta plus, mostly just a bare nucleus. So we could say that this base is loving of nuclei. Remember, nuclei are positively charged, so that base is nucleophilic. And in organic chemistry, we're going to talk a lot about nucleophiles and electrophiles. And another synonym for a nucleophile is a Lewis base, and a synonym for an electrophile is a Lewis acid. So we'll talk more about those in chapters 4 and beyond. Thanks for listening.